In the last lecture, we saw how to reduce any matrix whose entries are in a Euclidean domain to Smith form. The same thing can be done over a principal ideal domain, but the algorithm is a little more involved. So let me explain what modifications are required to work over matrices with entries in a principal ideal domain. So if you recall the algorithm, one of the steps was that you had a matrix and we were trying to clear out the entries of the first row and first column. So we had this matrix like this, and then the first row and first column had some entries. And for the moment, let's just focus on trying to clear out the first row. Say there's some entry here, A1j, in the first row and jth column that we want to clear out. And so when we were in the Euclidean domain, we were looking at the case of trying to clear out A1j using A11, and failing which we would somehow try to reduce the size of A11. So we had the case where if A11 divides A1j, then you just do Cj goes to Cj minus Q C1, where A1j is equal to QA11 A1j. But if A11 does not divide A1j, then what we did was we used the Euclidean algorithm. So then what we know is that A1j equals QA11 plus R, where D of R is strictly less than D of A11. And then what we did was we did Cj goes to Cj minus QC1, and then we got R in this position over here, and then we interchanged Cj and C1. So let me show you how to modify these steps when we don't have Euclidean domain, and therefore we do not have the Euclidean division algorithm. So if A11 divides A1j, then all is well. We can just use this step to clear out A1j. But if A11 does not divide A1j, so suppose now R is a PID, not necessarily a Euclidean domain. Then what should I do? So firstly, what I know is that if A11 does not divide A1j, then that means that A1j is not in the ideal generated by A11. That means that the ideal generated by A11 and A1j is strictly larger than the ideal generated by A11. On the other hand, we are working in a principal ideal ring. So this ideal is generated by a single element. So let R be such that R actually generates A11 and A1j. Okay, so what that means is that R lies in the ideal generated by A11 and A1j. So what we have is that R is equal to A11 times X plus A1j times Y, and also R divides A11 and R divides A1j. Well, this means that I can write A11 as Q11 times R, and this means that I can write A1j as Q1j times R. So what I get is 1 is equal to Q11 times X plus Q1j times Y, just taking this first equation and dividing both sides by R. So we have this. And now what I'll do is I'll construct a matrix T. So instead of doing column operations, I'm going to be right multiplying by this matrix T. And this matrix T is of the following form. In the 1 1th position, I'm going to put X, and it's going to have mostly zeros everywhere, but in the jth row here I'll put y, and then I'll have identity ones along the diagonal, except now again in the jth row and jth column I'm going to put a11, and over here I'm going to put negative of a1, not a11, q11, and here I'm going to put negative of q1j, and I'm going to continue with the ones over here, and this is going to be an n by n matrix with entries in R, and everything else in this matrix is 0. Okay, so zeros everywhere. So the only interesting, it's basically the identity matrix, except for the two diagonal entries are changed to x and q11, and the corresponding off diagonal elements are y and minus q1j. Then note that determinant of t is equal to, well, it's basically the identity matrix. The only thing that matters, the determinant of this 2 by 2 block. So it's x times q11 plus y times q1j. So determinant of t is 1, which implies that t belongs to GLN R. Now, if you do A goes to instead of doing a column operation, you take A by AT. Then what can you say about the matrix AT? Then the 1/1th entry of AT. What will be the 1/1th entry of AT? So to get the 1/1th entry of AT, I have to take the first column of T and I have to multiply it by the first row of A. And what I'll get is A11 times X plus A1J times Y. So I'll get R over here. And I don't really care what I get anywhere else. The point is that the ideal generated by R strictly contains the ideal generated by A1. And A is equivalent to AT because T is in GLN R. So this is the modification that we do to clear out entries, say in the first row, in the induction step of computing the Smith canonical form. But it's not, the result is not exactly the same. Earlier what we did is we found R such that D of R is strictly less than D of A11. But here we are just finding R such that the ideal generated by R is strictly larger than the ideal generated by A11. So one more modification is needed. So of course this kind of modification you can do even if you want to clear out all the entries of the first column, and so that's basically the only times that we used the Euclidean property, when we wanted to clear out the entries of the first row or the entries of the first column. But the result is also not quite the same. Instead of getting an element whose size is strictly less, an element in the 1/1th place whose size is strictly less than the element in the 1/1th place that we had earlier, now we have an element in the 1/1th place whose ideal, which generates an ideal that is strictly larger than the ideal generated by the element in the 1/1th place earlier. So for Euclidean domains, we had this trick to show that the process of trying to clear out the first row and first column must stop after finitely many steps with success, because we cannot indefinitely keep reducing the size of an element of the Euclidean domain. For PIDs, we will just use the Noetherian condition. So for Euclidean domains, we used the fact that dA11 cannot be reduced indefinitely, because it starts with some finite value and then we know that the values it takes are all non-negative integers. So if you reduce it a finite number of times, you cannot reduce it any further. So for general PIDs, we will use the fact that a PID is a Noetherian ring. Cannot be enlarged indefinitely, because then you would end up with a chain of ideals, an increasing chain of ideals that doesn't stabilize. And so the process must stop after finitely many steps.